So today I will present my recent work, which Markus already has said. It's a direct sampling SDR with a very high speed. Okay, so all right. With a very high sampling speed of 250 megasamples per second. So first of all, I would like to talk a little bit about direct sampling techniques. So direct sampling means that we try to put the analog to digital converter as close as possible to the antenna, so it can be considered as the holy grail in SDR by directly sampling the signal at the antenna. And basically, so the whole processing of signals, the whole reception is then done in the digital domain, which gives a lot of different advantages over analog processing. For example, we don't have any noise in digital signal processing. So the noise figures of all our parts in the receiver would be 0 dB. It's possible to implement almost perfect filters in digital signal processing with a very steep transition, with very high stop band attenuation, and the same holds true for amplifiers, where we don't have any distortion when we amplify a digital signal. Oscillators can be implemented with a very pure spectrum, and even mixing is just simply multiplication, which can be done perfectly in a digital domain. We don't have problems like aging of parts, we don't have EMC problems. You can open the box containing the receiver and it will not change the behavior. We have not such problems like impedance matching. And something that is sometimes overlooked is that digital receivers can be copied easily. So you can you can build a receiver, maybe in GNU Radio, you can send it to someone else, he can modify it, send it back to you, or you can make a backup of your receiver, you can make some changes if you don't like them, if the radio doesn't work anymore, you can just copy it back, something you cannot do in the analog world. The only problem which we have here, everything is just a matter of complexity. So for getting a very high performance radio, you need to invest complexity. But since the microchips become more and more better, more and more complexity is allowed, this is not a problem anymore today and will be even relaxed in the future. Okay, so the Panoradio itself, as I already said, it has a sampling rate of 250 megahertz. So the reception here is from 0 to 100 megahertz. Theoretically possible would be 125 megahertz, but since an anti-aliasing filter is required here, the reception goes only up to 100 megahertz. There's also an experimental setup which allows to do a direct sampling of 70 centimeter signals, so signals in the range of 430 megahertz. The radio itself, it features zoomable waterfall displays. It has 2 independent audio receivers, and the whole radio is implemented on a Zyng and Zedboard system I have presented last year. So it's an embedded system which, where you don't require any external PC. You can just attach a mouse, can just attach a monitor, and the radio is fully operational. On the radio itself, there is an operating system running. It's a Linux system. The Linux systems also allows you to run any software, any general purpose software which is available for Linux on this software-defined radio device. The signal processing itself here is designed for a maximum performance, so having very large bit width and having very good filters implemented. Here you can see the GUI of the Panoradio. You can see the 3 waterfall displays, which are here zoomable in 14 steps, so you can inspect signals very closely, but you also have this very wide range of signals that you can monitor. For example, here's the full span where you can see the AHF band is just on the left-hand side. And on the right-hand side, you can already see the VHF signals from the German broadcast stations. The heart of every direct sampling SDR, of course, is the analog to digital converter, and it's crucial to choose a device which has very good properties. The device I use here is the AD9467 from Analog Devices, which has 16 bits. From the 16 bits, there are 12.3 effective number of bits with an SNR of 76 dB. SFDR is 100 dB, so this is very good. And what is also very good is the analog bandwidth here. So the 3 dB bandwidth of the analog input is 900 megahertz, and it's with this device possible to do direct sampling even for several gigahertz if you tolerate some decrease in amplitude. I'm using here an evaluation board from Analog Devices, which has some additional features, some additional parts on it. One very important thing is the clock generator, because the clock generator needs to have a very low jitter not to introduce any additional noise. Here what is used is a Vectron VCC6 with a jitter of 133 femtoseconds, and the noise that is introduced by this clock jitter is here minus 80 dB, which is below the 76 dB of the AD converter, so this is perfectly fine. There's also an optional preamplifier and some parts for impedance matching and signal balancing. Still, in a direct sampling receiver, some analog parts are required, mainly for two purposes. One is to prevent aliasing happening by using appropriate filtering. And the second thing is you may increase the signal level. The Panoradio has 3 signal paths, one for the reception from 0 to 100 megahertz, which consists of 2 90 megahertz low-pass filter from Chrystek here. And these 2 low-pass filters together have an attenuation of 110 dB, which is quite a lot. But for an SDR, in the worst case, this is something that will be required. Also, some front end for the 70 centimeter signal path. So here there are 2 bandpass filters from Foxtec, plus an additional low noise amplifier, the LNA for all, which is a quite cheap but very good device. And third, there's a direct path for doing some further experiments for receiving also other signals. When it comes to the processing hardware, there are 2 possibilities. One is you can use an FPGA, the other one is you can use a processor. An FPGA is a microchip that contains a digital circuit that you can design, for example, by using a language like VHDL. And the advantage of an FPGA is that it provides very high processing speed, because an FPGA can do calculations highly parallel. And furthermore, it's also a usually small device requiring low power. The disadvantage is that the design is quite challenging, and it's also quite challenging to have some interfaces to the user, like to attach a monitor or to attach a keyboard or something like that. In SDA, you probably would use an FPGA to do some mixing, down conversion, high-speed filtering, or high-speed FFTs. A processor, on the other hand, it executes software. So this is very, very good for having a high flexibility. You can exchange the software very quickly in such a system. It's very easy to program a processor, at least in comparison to programming FPGAs. And if you use an operating system, you can attach a lot of different interfaces, a lot of different other devices. However, a processor is slow in its processing speed. So for SDA, you would probably use it for demodulation, for attaching some interface devices, or for controlling the receiver. So in summary, the ideal hardware for a high-performance SDR would be a combination of both, having an FPGA and having a processor. So we have heard about this device, about the Zyng device, today several times. So Xilinx announced this chip, well, they actually delivered these chips since several years. It's a hybrid SoC containing an FPGA and dual ARM core. It's currently a big hype in industry. A lot of companies are interested in such devices, and it's also very good for use in an SDR. What is also here important is that this device also has some I/O modules, so you can easily attach memory, you can have an interface to the SD card, and also attach USB devices. It's not only Xilinx that produces this chip, but also there is the competing company Altera. There the device is called Altera SoC. So this is the Zedboard. The Zedboard is simply an evaluation board for the Xilinx Zyng, which adds some very important parts like 512 megabyte DDR3 memory. There is an audio codec, Ethernet interface, HDMI connection for attaching a monitor, USB. There's an SD card slot. So there's a lot of things you can do with that. Also, what is quite important on the right-hand side here is the FMC connector. The FMC connector is a connector where you can put on additional modules providing additional functionalities. Okay, here a look at the box of the Panoradio SDR. It actually consists of a Zedboard. Zedboard provides all the interfaces to the outer world. And what is attached using the FMC connector here is the analog devices ADC board, which does the sampling, and all the coax cables and other parts you can see here, they are part of the analog front end. The signal processing in the Zyng is, as I already said, divided in an FPGA part for high-speed processing, and there is a slow-speed processing in software using the processor. I'd like to pick out one of the parts here, which is the waterfall DDC. So the purpose of the waterfall DDC is to provide the zoomable display of a portion of the spectrum. So it cuts out a specific bandwidth, stores the IQ data in a memory, then the processor takes this data, does an FFT, and presents the result of the FFT in the GUI. The crucial question is, how can one implement the flexible bandwidth here in this DDC? Because there are 14 different steps going from, let's say, 100 megahertz down to several kilohertz. So should we implement a very complicated or a large number of FIR filters? Well, actually that's not necessary. It can just be done by changing the decimation rate in the CIC filter. And the FIR filter stays fixed. So all in all, this is from a complexity point of view a very good solution. In total, there are in the GUI 3 different waterfall displays. So does that mean we need 3 different DDCs? Actually not. So what I have implemented here is I took these 3 displays and multiplexed them onto one DDC. So the DDC is basically changing its frequency several times per second. And this is possible here in the digital domain because digital receivers are very agile in frequency. Here again, you can see the filter bandwidth of the DDC for the zooming FFT. The CIC rate is increasing from right to left. And here the attenuation is more than 100 dB. So you really get a very clean spectrum without any artifacts coming from the DDC itself. Okay, so in the final implementation here, in the FPGA, the ADC interface is implemented, the DDCs, and also some audio demodulation, which has been done with the Viva method. The FPGA is designed with the Xilinx Vivado software. Some parts of the receiver are implemented by using Xilinx IP cores, for example, CIC filters, FIR filters, or DDS. So there are very good blocks already available from Xilinx, and some blocks I have designed with VHDL on my own. The processor executes a GUI, controls the radio, does an FFT, and it can run general purpose demodulation software just like FLDIGI. The programming has been done in C++ using the Qt library for GUI and QWT, the FFTW library, and on the SD card there is a Linux Linaro running. Here you can see the layout of the FPGA system for the different blocks. And if you have a look at the resource utilization, you see that this FPGA is even less than half full, so there's a lot of space left to implement additional functionalities. And this Zyng chip is really a rather small device from an FPGA point of view. So you can imagine what is possible from a complexity point of view in future FPGAs. Okay, at the end, some reception examples. Here you can see in the main waterfall display the whole shortwave spectrum. The smaller left one, waterfall, shows a 20-meter band, and here I have extracted some PSK31 signals, which can be decoded right away with FLDIGI on the right-hand side, and all the software is running on the same hardware. Since the sampling rate is so high, we can also do direct sampling of broadcast signals, here from 88 megahertz to 100 megahertz. Here on this zoom on the, I think it's a 25-meter broadcasting band, and the smaller waterfall plots, they are zoomed in on specific signals. So these displays are all independent. You can tune them to very independent frequencies. Yeah, and here full zoom on Digi mode in 20-meter band. So again, a lot of PSK signals, and on the right side, maybe some MFSK signals. Yeah. To give you an idea what you can do with this kind of radio. Okay, so that's the end of my talk. Thank you very much. I've also put up a website, panoradio-sdr.de, where you can find all the information I've talked about now, and you can even find more information. In the next couple of weeks, I'm also planning to put all the software and hardware parts online, so you can learn from it, you can comment it, or you can even improve it. So thank you. Zedboard is. Oh, that's more. That's cheaper than I bought it. Okay, I bought it several years ago. It was like 250, 300 euros, something like this. Yeah. Yeah, and it's more expensive than the Zedboard, I can tell you. So it's maybe 300, 400.
And you can actually try to like build such a board yourself, but you end up shooting yourself in the foot because that's a multi-layer board with a lot of experience going into it. Then.
But if you're experienced with that, and if you like, you can build your own board. I mean, other people did it as well, of course. And also the analog front end, like the 90 megahertz low pass filters, they are not so cheap. So I guess it was like 40 euros. You have two, then it's again 100 euros. You have this metal box, you have the coax cables, you have the coax relays. So in the end, maybe a little bit less than 1,000. But it's not optimized for cost. It's like a tech demo. I wanted to show what is possible. So if you want to have a more cheap thing, you definitely can make it cheaper.
With a system like that, you're oversampling maybe let's say 25 kilohertz channel with a factor of 1,000 to 10,000. So this really means that you're getting an SNR gain out of audio oversampling that is pretty much impossible for anything but such an intensely oversampling SCR receiver, right? And for that, it's kind of cheap.
Can you? Okay.
Yes, is your radio also suitable for quadrature downconverted signals from, well, above a gigahertz bands with IQ downconverted signals?
The analog
you need two channels then.
Pardon?
Then you need would need two channels to digitize.
I mean, at the same time, you have to multiplex it. Yeah, you need. The problem is always the analog front end. Okay, if you want to do like bandpass sampling, you always have to cut out the right portion of the spectrum in the analog domain. Yeah. So this is always the crucial part. And this is also a problem direct sampling will not solve.
Okay, any more questions? I see no more questions. So then, thank you very much, Stefan, for this highly interesting talk. Applause for Stefan, please.